The pursuit of artificial general intelligence centers on a single, omnipotent digital brain. For enterprise strategy, however, that goal is secondary to deployable utility. Management teams prioritize economic utility over a model's IQ score. Organizations seek results, fewer errors, faster response times, and higher throughput across specific work tasks. This requirement defines useful intelligence. It is the specific capability to reliably convert context into action, while operating under strict parameters of cost, privacy, and reliability. A system provides this value through 5 traits. It understands the task context and accesses secure data without violating permissions. It executes actions within a workflow, escalates failures to a human, and generates a measurable audit trail. A frontier model that writes a brilliant strategic analysis remains an overhead cost if it cannot touch a company's ERP system to resolve a business task. The AI revolution has reached a turning point. The initial race to build the smartest model is being replaced by a race to deploy adequate intelligence wherever work happens. This evolution begins with cognition. In this stage, models master language, summarization, and pattern recognition, which establish the baseline for what AI can understand. The second stage is coordination. AI becomes an agentic layer that manages work across software systems and human approvals, shifting the technology from a chatbot into a tool for execution. The third stage is embodiment. Intelligence moves into physical systems, guiding industrial equipment and robotics to perform mechanical labor in real-world environments. These stages overlap. A single organization might deploy email summarization in its marketing department while simultaneously testing robotic pilots in its logistics centers. As intelligence moves through these stages, it stops behaving like a standalone application and begins to function as a distributed operating layer. In July 2026, AI models are capable of high-level digital work, but enterprise deployment remains experimental and fragmented across most industries. This chart reveals the economic engine of the next decade. While model capability on real-world tasks is rising, the cost of inference is falling sharply, according to data from MIT FutureTech. These falling costs trigger an explosion in usage. As tokens become cheaper, companies deploy more agents and more complex workflows, increasing the total volume of AI embedded into their products. The immediate value exists in language-heavy digital tasks with clear workflows, such as IT ticket triage, automated document extraction, and contract review. In contrast, open-ended physical environments and high-stakes unsupervised decision-making remain immature. The current reliability gap makes these areas a secondary priority for 2026. Management teams must build their data hygiene and governance habits within these bounded digital environments first to prepare for the larger shift. The actual path of enterprise adoption is dictated by the economics of the cost per completed outcome, not just raw intelligence. Between 2026 and 2028, we enter the deployment race, where the focus moves from the laboratory to the workflow. Access to frontier models is now table stakes. The primary friction for a company is translating messy human operations into clean, agent-ready digital workflows. A model without proprietary company data is a generic consultant. To become operational, it requires deep context, customer history, and explicit access to enterprise records. This evolution forces enterprise software to change. Traditional platforms that only provide screens for humans to click through are being rebuilt as workflow control planes.
A control plane maps the state of the work, manages security policies, and provides AI agents with a governed pathway to take action safely. In this phase, the advantage belongs to the platforms that own the workflow graph, making intelligence both actionable and auditable. From 2028 to 2030, the market shifts to inference industrialization, where the priority is deployment economics at scale. Executive strategy becomes disciplined. Organizations prioritize the cheapest reliable intelligence layer that can complete a given job well enough. Routine tasks migrate away from premium cloud models toward local devices, private company servers, and neural processing units in PCs. Hyperscalers begin deploying custom ASICs designed for specific high-volume tasks, reducing the reliance on general-purpose hardware for stable workloads. At the extreme end of this efficiency drive, we see model-specific silicon. Stable algorithms are hardwired into silicon, effectively turning an AI model into a specialized hardware appliance to slash energy and latency costs. When capability crosses a threshold of good enough, the market begins to compete on cost, convenience, and energy efficiency per watt. Between 2030 and 2035, the embodiment race takes digital intelligence into physical reality. Physical AI is the fusion of perception, reasoning, and real-world mechanical control. A system must sense an environment, simulate outcomes, and execute motion through actuators. The primary constraint is Moravec's paradox. Tasks that are computationally simple for digital AI are often immensely difficult to execute mechanically in unstructured environments. Because of this paradox, initial deployments favor specialized robots in bounded environments rather than general-purpose humanoids in homes. Factories, warehouses, and logistics centers offer the controlled variables and measurable ROI required to justify this transition to physical automation. This shift creates a massive physical infrastructure requirement for advanced packaging, modular power blocks, and edge cooling systems. The embodiment race transforms the physical infrastructure of the economy, completing the transition from digital reasoning to real-world action. This architecture represents a hybrid system, diverging from the vision of a single monolithic AI brain. The top tier is frontier AI, reserved for hard reasoning, complex agentic workloads, and the most challenging scientific problems. Below it, the company private layer manages institutional knowledge, while the local device layer handles low-latency, privacy-sensitive personal tasks. Finally, the edge and physical AI layers provide real-time machine intelligence and manage robotic motion in factories and warehouses. The agent and workflow control plane coordinates the entire stack, managing the routing of tasks, data permissions, and the required human approval steps. Success in the next decade depends on intelligence allocation, matching every task to the cheapest, safest layer of intelligence that is adequate for the job. Long-term value belongs to companies mastering workflow orchestration and private knowledge layers. Thin AI wrappers and generic chatbots face inevitable obsolescence. Moving past the novelty phase, management teams will replace the pursuit of academic benchmarks with a focus on business ROI and faster cycle times. True AI readiness requires the unglamorous work of mapping organizational workflows down to the permission level before an agent ever touches the system. As this sweeping technological transformation accelerates, AI moves from impressive to useful to ubiquitous and eventually to embodied. By 2035, the most valuable companies will be those who own the deployment points of useful intelligence. The industry narrative assumes scaling AI requires routing every business function through a single monolithic frontier model. In practice, that architecture cracks under operational reality. The first constraint is economic. As inference usage expands, sending every routine task, like closing an IT ticket or summarizing a meeting, to a massive cloud model ensures the cost of compute will quickly erase the financial value of the automation. The second constraint is latency. Real-time physical operations, from autonomous industrial sorting to high-frequency digital workflows, cannot afford the delay of a round-trip query to a distant server farm. Split-second decisions require local execution. Governance creates a strict data boundary. Corporations cannot send proprietary codebases, unreleased product designs, or regulated customer records to public data centers for general inference without violating compliance and security protocols. Finally, the physical infrastructure itself poses a hard limit. With global data center electricity consumption projected to reach 945 terawatt-hours by 2030, a strictly frontier-only strategy is ecologically and logistically unviable. Relying solely on a massive cloud model is an architectural dead end. The enterprise requires a different approach, intelligence that is context-aware, affordable, and heavily distributed. Over the coming decade, the race shifts from the pursuit of the smartest theoretical model toward the effectiveness of its deployment points. Useful intelligence functions as a deployed business capability, one that reliably converts context into action while operating within specific cost, latency, and privacy constraints. This diagram outlines the useful intelligence deployment stack. It presents a heterogeneous, multi-layered architecture where compute is allocated based on the specific demands of the task.
The core operating principle here is discipline. Organizations must deploy the cheapest, safest, and most adequate intelligence layer available for a given job, not default to the largest model. The market advantage over the next 10 years belongs to the architects who can orchestrate this distributed operating layer across the physical and digital economy. Looking at the top of this stack, Frontier AI layer represents the premium intelligence tier. This cloud-heavy layer is reserved for deep scientific discovery, complex coding, and multi-step agent creation. It is utilized only when the high cost of a highly capable answer is economically justified. Directly below is Company Private AI. This tier secures proprietary context, internal policies, deal flows, and customer records, keeping institutional knowledge safely within protected enterprise boundaries. The third tier, Local Device AI, shifts computation directly to neural processing units on laptops and phones. This handles privacy-sensitive, low-latency tasks like local document reasoning without ever pinging the cloud. Edge AI pushes intelligence out to the physical perimeter. It sits near sensors and cameras in factories, energy grids, and hospitals to execute real-time local decisions where bandwidth or latency constraints prohibit cloud reliance. At the base is physical AI. This is the embodiment layer, placing foundation models inside robots and autonomous machines that must perceive their environment, navigate safety constraints, and execute mechanical actions. Beneath these 5 is a structural 6th layer, model-specific silicon. For exceptionally stable, high-volume workloads, the algorithms themselves are hardwired directly into custom chips to achieve extreme operational efficiency. Distributing compute across these tiers solves the physics and privacy bottlenecks. However, it creates a massive orchestration challenge, determining exactly where and how a specific task should run. This vertical block represents the agent and workflow control plane.
It provides the governance and logic required to make the horizontal tiers functional. Its first function is dynamic model selection. As a request enters the system, the router evaluates the complexity and automatically assigns it to the cheapest adequate layer. Next, it enforces permissions and data access. The control plane ensures that an autonomous agent cannot bypass identity protocols, use unauthorized tools, or view restricted company data. It also manages human approval and audit trails. When an agent attempts a high-risk action, the control plane suspends the workflow, requests human authorization, and logs the outcome to measure direct business ROI. If a company deploys models without this orchestration layer, the result is chaotic AI sprawl, duplicated compute costs, untracked shadow agents, and zero visibility into process failures. Because it governs the execution of work across every underlying tier of intelligence, the control plane is the most strategically valuable territory in the modern enterprise stack. Understanding the architecture is only the first step. Companies must also accurately map these capabilities against a practical timeline. This matrix separates proven utility from market noise. In the green column, immediate value lies in bounded digital workflows, automated code assistance, local device privacy tasks, and company-specific document extraction. In the near term, utility scales rapidly into agentic workflows. AI stops merely drafting text and begins diagnosing tickets, checking policies, and moving complex business processes forward autonomously. Conversely, the orange column reveals what is quickly losing relevance. Thin chatbot wrappers disconnected from internal data are becoming obsolete. The market no longer rewards raw benchmark scores. It demands deep workflow integration and measurable outcomes. Looking at the deployment timeline out to 2035, the focus shifts to physical environments. Industrial robotic fleets scale up, and intelligence cements itself as a distributed operating layer across the physical world. The scarce resource is no longer the raw capability of a foundation model. Economic value has migrated toward the systems of action that govern them. This shift resolves the ongoing debate over whether AI agents will render traditional enterprise software obsolete. Software that merely provides a static dashboard, relying entirely on humans clicking through forms, will be aggressively hollowed out by AI abstraction layers. But control plane SaaS, platforms that maintain the workflow graph, strict user identities, and audit trails, becomes indispensable. AI agents cannot operate in a void. They require these established systems of action to navigate enterprise environments securely and legally.
Platforms like ServiceNow and Salesforce are already pivoting, positioning their core architectures not as screens for humans, but as governed execution fabrics for agents. Enterprise software survives by evolving. It transitions from a database that records what happened in the past to the engine coordinating what an agent must do next. Over the span of a single decade, AI progresses from digital cognition to enterprise coordination and finally into physical embodiment. The winning architecture abandons the monolithic cloud approach. It scales by placing adequate, cost-effective, and highly trusted intelligence exactly where the work is happening. Efficient adoption requires moving past intelligence as a novelty feature and building it as a fully integrated, distributed operating capability. This deployment stack represents the complete physical and digital infrastructure required to make intelligence functional. By 2035, competitive advantage is determined less by the IQ of a model and more by the ownership of its deployment points.
Direct, analytical tone. A very specific myth dominates corporate strategy right now. Executive teams assume they can cancel their existing software subscriptions, buy access to massive cloud GPU clusters, and let artificial intelligence figure out the rest. But the data reveals a severe paradox. Frontier models are undeniably becoming smarter, passing advanced reasoning benchmarks and accelerating in capability. Yet actual corporate return on investment is stalling, exactly at the point of deployment. The root cause is structural. An AI model that scores highly on an intelligence test but lacks access to your proprietary customer records, your internal permissions, or your workflow triggers is functionally useless to your business. It is a brilliant consultant trapped in a sealed room. Between 2026 and 2035, the primary strategic objective shifts from training the smartest model to deploying adequate intelligence at scale. Extracting true enterprise value requires abandoning the idea of bolting thin chatbot wrappers onto old processes. It requires completely redesigning both the software governance layer and the physical hardware stack underneath it. This image captures the physical bottleneck of the current AI architecture: hyperscale data centers packed with high-density server racks. The extreme power demands required to train and run frontier AI models are threatening to overwhelm local grid capacities. The capital expenditure required to build, cool, and power these facilities is climbing into the trillions of dollars. Because of these extreme physical and financial constraints, it will be economically impossible to route every routine daily enterprise task through a centralized supercomputer. The math simply does not support using massive cloud clusters to generate simple email summaries or internal ticket updates. The industry is being forced toward useful intelligence. This means AI that is affordable, trusted, and integrated enough to actually execute a business outcome without triggering a massive compute cost for every prompt. Once models cross the threshold of being good enough for standard knowledge work, the scarce resource in technology stops being raw intelligence. The scarce resource becomes deployment efficiency. This chart separates AI applications creating value from those becoming obsolete. Fading out, thin chatbot wrappers, cloud-only inference, and benchmark worship. They generate novelty, not durable ROI. Scaling up, model routing, private knowledge layers, and local AI. These prioritize privacy, latency, and integration. We are witnessing the maturation from cognition to coordination. Cognition is an AI answering a question. Coordination is an AI autonomously moving a multi-step process forward. A concrete example of coordination is an AI agent reading an IT ticket, cross-referencing your specific company policy, writing a script to fix the issue, and then independently routing that script to a human manager for final approval. Standalone foundation models will eventually stabilize into standardized utilities, much like bandwidth or electricity. The primary drivers of enterprise wealth will be the integrated agentic workflow systems built on top of them. This brings us to a major industry misconception: the assumption that if an AI agent can operate software through an API, traditional enterprise SaaS interfaces are dead. What dies is weak SaaS, legacy software dependent on humans clicking buttons. Because AI agents now operate these interfaces, that human click layer is obsolete. Instead, control plane SaaS becomes critical. Modern platforms evolve into active workflow graphs that verify identity, enforce permissions, and maintain audit trails.
These control planes are strictly non-negotiable. Autonomous AI agents require these exact software guardrails to operate safely, legally, and predictably within a heavily regulated corporate environment. Enterprise SaaS is bifurcating. The human-facing user interface will fade away, but the underlying workflow graph becomes the enterprise's central system of action. If software control planes determine how AI is allowed to act, the physical hardware determines what those actions actually cost. Enter inference industrialization. As companies deploy millions of automated agent workflows, they face an operational mandate to ruthlessly minimize the financial and electrical cost. The sheer volume of daily routine tasks, like extracting data, drafting standard emails, or triaging alerts, makes it economically ruinous to process them all on expensive, power-hungry cloud frontier models. This relentless economic pressure to lower compute costs permanently fragments the hardware market. The era of the GPU monoculture is ending. In a mature AI economy, deploying adequate, specialized intelligence cheaply yields significantly higher margins than deploying peak, generalized intelligence expensively. The 2030 enterprise requires a diversified hardware architecture. GPUs remain the heavy-duty engines for complex training. CPUs serve as the control plane for system orchestration. NPUs become the default for local, privacy-sensitive tasks on endpoints. Finally, custom ASICs and model-specific silicon emerge as hardwired appliances for maximum cost efficiency at massive scale. The 2030 hardware stack operates as a diversified portfolio of specialized chips, all optimized to drive the marginal cost of a completed task as close to zero as possible. Combining software control planes with specialized hardware reveals how successful deployment operates. A request hits the SaaS control plane, instantly verifying identity and data permissions. The system then intelligently routes the task away from expensive cloud GPUs to local NPUs, keeping proprietary data secure. Finally, the specialized hardware executes the action and logs a permanent, immutable audit trail back up to the software layer for compliance and measurement. This seamlessly integrated stack, moving from strict software governance down to the exact cost-optimized microchip, is the only way businesses will extract safe, measurable ROI from artificial intelligence. The era of relying on hype, raw benchmark scores, and disjointed software wrappers is over. The corporate winners of the next decade will not be the organizations that simply purchase the most compute or deploy the highest volume of chat interfaces. Competitive advantage belongs entirely to the teams that master deployment architecture. Mastering this architecture requires 3 specific actions: mapping clean internal workflows, establishing rigid SaaS control planes, and intelligently routing tasks to the cheapest, safest hardware layer available. Useful intelligence now functions as a distributed operating layer, woven directly into the software, hardware, and physical infrastructure of the global economy.
Winning in AI now depends less on raw model intelligence and more on the ability to manage its deployment where work actually happens. Right now, there is a pervasive assumption about how to implement AI in a business. It usually looks like this: route every company task, big or small, to a massive centralized frontier cloud model, all accessed through a simple chat interface. That monolithic approach breaks down inside a complex organization. A frontier model might write a brilliant strategic synthesis, but if it cannot touch internal systems, access proprietary data, respect user permissions, or trigger an approval workflow, it remains disconnected from actual operations. Useful intelligence describes a specific business capability, the reliable conversion of context into economically valuable action within the constraints of a real-world workflow. If a model is not directly connected to a workflow control plane, it remains an impressive software feature. It fails to become a business capability that generates a return on investment. To build that capability, we have to clear the board. By 2030, several current implementation practices will become completely indefensible. Thin AI wrappers are the first to drop off. A product that simply adds a prompt box to someone else's model without proprietary data, deep workflow integration, or strict governance has no defensive moat. This chart illustrates the economics of scale. Relying on pure cloud inference for every minor, routine task creates an exponentially rising cost curve as token usage explodes. Meanwhile, the cost of executing those same high-volume tasks on local NPUs flatlines, making cloud-only routing economically irrational. Software design also shifts.
Enterprise software that assumes a human will manually click through forms and dashboards will be abstracted away. Agentic workflows require systems of action, not screens designed for human clicks. We will also see the end of benchmark worship. Standardized testing scores do not matter if they are decoupled from actual business metrics, like cycle time reduction, lower defect rates, and optimized inventory. Companies sitting on massive data hoards will find them useless to AI if they lack strict, clean permission structures. AI needs usable context, not a messy, unregulated storage drive. This table outlines what becomes useful versus what fades. The fading practices on the right share a common flaw, lacking deep enterprise integration. Instead, the left column shows focus moving entirely towards orchestration, model routing, and workflow control planes. The scarce resource is no longer access to raw intelligence. The bottleneck is the operational hygiene required to deploy that intelligence safely and profitably. The solution to the broken monolith is a hybrid intelligence portfolio. It is built across 3 distinct tiers: process, control, and infrastructure. Starting with the process layer, the first operational step is mapping detailed workflows, not buying models. AI agents require deterministic maps to function safely. They need a documented path that traces a request, flags an exception, secures an approval, takes an action, and generates an audit log. The second step is building a private knowledge layer. This means cleaning and connecting proprietary data, policies, customer records, and operating history, so the AI actually knows your business. The strict rule here is that data without permissions is unusable context. If the system does not know who is allowed to see a document, the agent cannot be allowed to search it. As agents take over routine execution, human roles must be deliberately redesigned. Employees shift away from manual processing and move towards judgment, creative direction, exception handling, and system governance. Process hygiene is the mandatory foundation. An AI agent cannot safely automate an enterprise workflow that the enterprise itself does not fully understand or govern. This diagram outlines the useful intelligence deployment stack. Strict model routing allocates intelligence across 5 tiers. Routine tasks use local device AI. Proprietary tasks use company private AI. Public frontier AI is reserved for complex reasoning. Governing this requires an AI control plane across every layer. The final control step is establishing rigid evaluation systems. Every deployed agent requires a task scorecard, measuring accuracy, escalation rates, and actual return on investment. Without a strict routing and control plane, enterprises will drown in AI sprawl. They will suffer from duplicated inference costs, shadow IT projects, and massive security vulnerabilities. Beneath the software sits the infrastructure layer. We have to challenge the assumption that all future AI compute will live exclusively inside massive hyperscale facilities. Pacing slows slightly. Massive data centers remain vital for frontier training and large-scale synthesis, but they cannot efficiently support ubiquitous inference for every minor task. That necessitates a shift toward a heterogeneous hardware portfolio. Compute moves outward to local NPUs in workstations, rugged edge compute enclosures on factory floors, and highly efficient model-specific silicon for standardized tasks. This distributed compute physically changes how power is delivered. Because AI accelerators draw massive current, the focus shifts toward high-density modular power blocks and highly efficient rack-to-board conversion. Management teams must track macro-level grid constraints, advanced cooling architectures, and localized power availability just as closely as they track software updates. Modular distributed infrastructure ensures power delivery acts as a performance enabler rather than a system-wide bottleneck. The ultimate test of this hybrid architecture is projecting it against the highly constrained macroeconomic and physical realities of 2035. This matrix maps 4 specific scenarios that enterprise systems must be prepared to survive: the baseline, the bottlenecked world, fragmented sovereignty, and accelerated physical AI. First, the bottlenecked scenario. If grid failures occur and data center power constraints lead to prohibitive cloud costs, the architecture survives by relying heavily on its local NPUs and specialized power-efficient edge inference. Second, the fragmented sovereignty scenario. If geopolitics dictates strict data localization mandates and regional compute blocks, the architecture adapts because its company private AI layer already keeps sensitive data sovereign and internally governed. Third, the accelerated physical AI scenario. If we see a rapid scale-up in industrial robotics and autonomous systems, the architecture is ready to deploy edge routing and physical control planes directly to the hardware. This physical scenario is already taking shape today. Industrial environments with high-volume, bounded, and repeatable tasks are actively integrating perception and motor control. Resilience in the next decade comes from the ability to dynamically adapt to physical, grid, and geopolitical constraints. It does not come from merely licensing the smartest algorithm. Regardless of which scenario plays out, the future of intelligence is definitively heterogeneous and distributed. The evolutionary path of this technology follows a strict sequence. It began as impressive. Right now, it transitions to useful. By 2035, it becomes ubiquitous. And finally, it becomes embodied in the physical world. The organizations that win the decade will not be those that simply buy AI. They will be the ones that architect systems to place the cheapest, safest, adequate intelligence exactly where the physical work happens.